yangu venenge vachidzidziswa nayo setup iyi kudai yo.
What did you say?
Nodai vanhu vaiona setup yacho vanenge vachidzidziswa nayo.
Fucking found it.
Hello everyone. According to my time, it's now 5:15. So as usual, for those that are joining us for the first time, which from what I can see, I think I'm only seeing one new name here. I will try to be going as fast as I can since there's quite a lot to cover. And if it happens that you've got a question, there is a function here in the chat group. You are welcome to just write your question down in there. You can also use the reaction function down here to just get my attention, because it could happen that you've got a question while I'm facing this side. So you can just I choose either of the reactions that are in there, and then I'll give you attention, and then I'll answer your question. Okay, cool. So can I just to say that you're going what I was saying, can I just get a reaction as a go ahead for us to start? Awesome, cool. So, okay. Please just do allow me to start with something that's not necessarily on the agenda for this workshop, but it's still going to be part of your test, like since Melissa's section is covered in the test. And that is just a small thing under simulation that I just want to get out of the way. It's just like maybe 2 or 3 minutes of 5 or maybe 5 minutes of this session. And it's as follows, that initially when we spoke about simulation, right, that is generating random realizations of X, and would equate this here to U, of which this U was uniformly distributed between 0 and 1, like that. That is something that we agreed on. And then to generate the random realizations of X, we know that all we had to do was then to solve for X, and we would find that this here is equal to this like that. Then your conclusion would be to actually generate random realizations of X from the distribution. All you have to do is to let X be equal to that, where this here is uniformly distributed between 0 and 1. One of the things that we didn't mention was the fact that this function that you get here is got the same CDF. It actually has the same CDF as f of X. So remember, you'd have been given information about the random variable X, right? And you want to simulate random realizations from that random variable X. And you do this as we've done here, and you get this function. And it's just important that I wanted to point out that this here has got the same CDF as f of X, the CDF of this random variable X that you have here. That is the same CDF that you're equating this U to, like that. And also just paying attention to the fact that this U had to be uniformly distributed between 0 and 1, which means that whenever then you are given a uniform distribution which is not between 0 and 1, and you want to find a function such that it will give you the same CDF as your X here, what you first have to do is to transform your uniform and 0 and 1. I'm sure by now you guys know the reason why I am discussing this question with you guys. What I mean is that in a case where you're given a uniform distribution between 0 and 2, like that, and the question is asking you for a function g of u such that that function g of u here will have the same CDF as what? As an f of x that would have been given. Right? So this function, this f of x at inverse u is actually a g of u. So when you're asked for a function g of u such that the same function g of u there has got the same CDF as your x, it's simply asking you to follow this procedure here and find this function when you get to this point, the function you have here is actually your G of U. But also paying attention to the fact now, when you do this here, this U must be uniformly distributed between 0 and 1, of which in this case here, this is between 0 and 2, which means we actually would first have to transform this here to actually be between 0 and 1. So this is actually very important because for a very long time, when it comes to simulations and random realizations, we've mainly just been focused in the past papers and everything else, even in my year, all this section focused on was just finding random realizations. But now we've seen a new way where you're asked to find a function such that the CDF here is equal to that. And in transforming this here, you have your U being uniform between 0 and 2, which is just a length. And we want this to be between 0 and 1. And since this is a length, it means you can literally just halve it. Why? Because you want this to be uniformly distributed between 0 and 1. And therefore, you would introduce a random variable V being equal to half of U, right? U, which is on the length is 0 to 2, but now we are saying half it, right? This means that if you're given some function uniformly distributed between 0 and 3, which means we would have a 3 there, but we would only want it to be uniformly distributed between 0 and 1. It means we would actually then just divide this here by what? By 3. But in this case, this is uniformly distributed by 2, and thus this will be just half of what? Of your initial U, which means you now just follow the same process here, where you take the CDF of X, which will be given, you get a CDF of X, and then now, instead of letting this to U, because our U is uniformly distributed between 0 and 2, in this case, this square will be equal to what? To V. And all you just have to do is now to solve for your X, and you find your X will be equal to some function here, and now you have your V. And the function that you're going to get here will simply be your G of U. And one other thing which is important, and which is important in this case, is the fact that this G of U will have the same CDF of X, like that. I just thought that this is something important to get out of the way there, because it's actually the first time I've seen a question about realization being asked in this manner. So I just thought it was quite important to get it out of the way. So now that it's out of the way, we can quickly get into the business of the day, which we will start by looking at this parameter estimation. So we have our parameter estimation. So what we're basically doing here in this section, right? All we've been doing in the past sections, we've been dealing with distributions, we've been dealing with an X that's maybe exponentially distributed and whatnot, and with the lambda, we looked at Poisson distributions, we looked at gamma distributions. Now what this section tries to do is to try and estimate the parameters of those distributions that we've been dealing with. And there are various ways in which we do that, some more popular than others, but at this point it's quite important for us to go through some of them, most of all of them, because they can easily be asked in a test. Cool. So what we are doing is to estimate our parameters, right? We want to estimate our parameters. And the first method that I'm going to start, that we're going to look at first, is the method of moments estimate, Cool. So I'm going to quickly write some notes on this here, a small summary, and then we're going to go and look at some examples so that it's more practical. And the first thing that's important about our method of moments estimator, right, is that it comes in two forms. There are two steps in this form here. And the first one is for you having to calculate your theoretical moments, right? Theoretical moments. So in short, this method, what it does is for you to, you aim to find two functions, and then you're going to, when you have those two functions, you want to equate them such that you make the parameter of interest the subject of the formula. And the right-hand side of your equation here, when you equate, will be coming from a theoretical moment, and the other side will be coming from an observed moment. You get it from your observed moments. Okay, observed moments. And on the theoretical moments, you also have your unstandard. You will have your unstandard moments, your unstandard moments, right? Remember your unstandard moments, you can always just check this here on your notes before. Your unstandard moments are the one where you are going to have the expectation of your XR like this. So from there, we can quickly agree that with your unstandard moments here, when your R is equal to 1, right? We sometimes write them like this here. Your first unstandard moment is simply just equal to the expectation of X, and the second one is simply just equal to the expectation of X squared. So part of the challenging part under this section is that in most cases, you will require these two moments here. And part of the work that you put in is trying to find this here. Either it can be simply given to you, or you'll be given a function or a distribution rather, which is on your formula sheet, and you can simply find this, some of these terms here, like the expectation and the variance on your formula sheet. While we're speaking about the variance, when this is with unstandard moments, and we also have the centered moments. We have the standard moments, right? Which we know, which a standard moment is actually just described or is defined as being the expectation of X minus mu n to the power R, like that. And we know that this, when R is equal to 2 here, when our R is equal to 2, that just becomes our variance of X, like that. When we get to the observed as well, we also have the same thing. We will have, okay, I'm going to transfer this to this side of the board so that you at least can see what I'm writing. So when we get to the observed moments, we also start with our with unstandard moments, right? With our unstandard moments, where the first unstandard moment here will simply just be the expectation of X, but instead of writing it the way we did here, this will just be X bar, right? So the fact, this term of being observed and theoretical, it comes from the fact that this expectation here is this is the type where you calculate using your integrals and your summations, whereas this ones that are observed, this involves you being given some data and you're given 1, 2, 3, 1, 2, and 3, and you actually add them up together and you divide by 3. That's what your X bar is there. And your second is actually just okay, this is 1, 2, this is just 1 over n, the summation of xi squared, like that. That's your second unstandard moment. So this one here is in fact just 1 over n, the summation of your xi, like that, to the power 1. We also have the centered, right? The centered, okay? And then under the centered here, for our variance, the first one, okay, let me just start with the second, this one here. This is the most important one, which is just that you have your s squared, like that. Cool. And yeah, that's basically the small summary that I wanted to write down under this section here. Now, please pay attention to this. It's very important that in most cases, when you will be asked to just find the MME of some parameter, maybe it's just going to be theta or it's going to be alpha, right? Your starting point always is for you to use this following here, your expectation of X and your X bar. So if I give you information about a distribution, it's CDF or a PDF, and then I ask you to find a method of moments estimate of your theta, the first thing that should come to your mind is you finding the theoretical expectation of your X and your observed mean, which is equal to that, and simply solve for that, right? It can happen that maybe when you have these two functions here, none of them will be in terms of your theta, so it can force you to then maybe start taking the second moments, that's your X squared and this one there. But in most of the cases, most questions can actually be easily answered by that there. You would not need to go forward to the second moment. It's only when you want the MME, right, of your sigma that you straightforward consider the second moment, right? Which means you consider the expectation of X squared simply just being equal to 1 over n summation of your xi squared. So all I've just done here is that firstly, I am saying if you're asked to find the method of moments estimate of your theta, right? It's just a normal parameter. It might be theta or alpha. Take this here, expectation of X, either you're going to calculate it or to be given, or you can find it on your formula sheet, get that to X bar. If you're given data, great. You can punch in that data and actually equate this to a number and solve for your theta. But when you are given to find the MME of sigma or sigma squared, you can straightforward just go to use these two equations, this equation that we have here. Because for most of the other parameters, you start from the first moments, but for our sigma, because we know that when our R is to be 2, in this case here, we always consider the second moments, and hence we go on forward straight to this equation, and you would find that you will not always necessarily have to find what this term is, like calculating it using your formula, like your integration, but you just have to use the fact that we know our variance of x is simply equal to the expectation of x squared minus the expectation of x all squared, like that. So this is something that you need to always keep remembering, that you won't have to put yourself through the work of finding what this is here manually, because you can, if you have that there on your formula tape, on your formula sheet, and you can get that on your formula sheet, you can simply solve for that. And after having said all that, I want us to quickly go through an example, which will try to put all that I've said here in words by putting it in numbers. I can call them numbers. And it starts as follows. Right, and again, this is for this kind of question here, because most of these methods are actually very simple. The only work in them is that you will have to find expectations and your moments and whatnot, but most of the times they're very easy. And for the MME method, this is as worse as it gets, right? And as worse as it gets is actually simple, which just tells you that it's actually quite an easy approach. You're given the PDF of x as being 1 over beta minus alpha, and this is between, when our x is between alpha and beta, like this, then you're given this here as being 0 otherwise, right? So this is our PDF that we're given of x, and then what we need to do is to find the method of moments estimate. You need to find the method of moment of estimate of your theta, of your alpha, and also your method of moment estimate of your beta, like that. So this is what we need to find. And fortunately, this question here is explicitly given out to us that the expectation of x is equal to alpha plus beta over 2. And we're also told that the variance of x is actually just equal to beta minus alpha all squared over 12, like that. Again, this is telling us this here explicitly like this is actually a favor, because in some questions they will not even tell you this here, but I would rather want you to quickly recognize from this that this is a PDF of a uniform distribution, right? Where your x is uniformly distributed between alpha and beta, like that. Which means all you would have to do is to recognize that, okay, this is a uniform distribution. So now from now on, especially under this section, you also see the reason why I'm saying it's important when we get to this other method I want us to talk about. It's very important that you clearly look at your PDF. Like in this case here, the reason why it's important to look at it is for you to figure out that it's a uniform distribution, and therefore you can find these moments straight from your formula sheet as they are given here in this question. And you'll see why we are going to use this here. Because remember, I mentioned that when you want to find your MMEs, if it's not a sigma, the first equation you should turn to is the expectation of x the expectation of x, then this is alpha plus beta over 2, simply being equal to x bar, which we can simplify as being alpha plus beta being equal to x bar, 2x bar, like this, 2x bar. Okay, and the reason why I say this is as worst as it gets is because in this case here, we want to estimate 2 parameters, but in a very simple case, where we are estimating 1 parameter, suppose all we had to do was to estimate alpha, right? This is just this is not part of the question. I just want to show you an alternative to this question here, which could have simply been estimate alpha here. And we are given the expectation, again, assuming we are given the expectation that this is equal to alpha over 2, right? This means for you to find your method of moments estimate, all you just have to do is to first consider this equation, like I mentioned, your theoretical equal to your observed mean, which means you would have alpha over 2 being equal to x bar, and thus your estimate will just be equal to 2x bar. So this is basically, under normal circumstances, this is as easy as it is to find your MME or estimate. But in this case here, where now we are given two parameters that we need to estimate, we just need to do just a little bit more work, but nothing very complicated. So this will always be the first equation you tend to if it's not sigma. But because now we want to estimate two parameters, it also means we will need two equations, and then we're going to solve those simultaneously to find our estimates that we need to find. So if this here will not give us both our equations, it means we can then now turn to the second one. The second equation that I mentioned we would have to turn to, which is that the expectation of our x squared will simply be equal to 1 over n and the summation of our xi squared, right? So here, what I've just done, I was using our first moments, and then now here we're equating our second moment, right? As you can see, these are all just our unstandard moments, because I don't know, I've not really seen a question where I use the standard moments. Most questions just use where I use the standard moments. Most questions actually use the unstandard, and there are even specific questions which even help you to know that you don't need to worry much about the standard by telling you that find the MME of maybe the parameters using the second unstandard moments, for example. Like I've seen a question which specifically says using the unstandard moments, because since we have the two, maybe sometimes you may be wondering which was to use, but most of the times just turn to your second unstandard moment or your first unstandard moment if you are just looking for estimating one parameter. So now it goes back to us wanting to find what the expectation of x squared is in this case, okay? And the expectation of x, and again, it's very important now that even with any other distribution, whenever you want to find the expectation of the parameters like this here, you will just follow the same procedures. The only thing that will be different is your expectation and your variance. And the reason I'm saying this here is because there are a few tricks that we're going to introduce here, which may not necessarily be easy to think of, like in an exam if you were seeing for the first time. But the fact that we're going to go through them now, it's important just to keep them in mind. And whenever you need to estimate again two parameters, you just follow the same procedure. And now, so the equation we have here at hand is the expectation of x squared being equal to 1 over n and the summation of xi squared, like that. Okay, this here is not much of an issue, but what we want to first look for is what the expectation of x squared is. So for a distribution which you cannot find on your formula sheet or no, where you're given the expectation of x squared, you would have to go and actually manually calculate this here by using the law of the unconscious statistician. But in this case, we are given our expectation and we're given our variance, and we know that the variance of x is defined by the expectation of x squared minus the expectation of the same x but all squared. Which means in this case here, this expectation of x squared we're interested in is simply equal to the variance of our x plus the expectation of x all squared, like that, right? And the reason why we do this is because these terms are actually given, and now will just be a matter of substituting, right? Where now we're going to have beta minus alpha all squared and 12 plus, okay? And like I was saying, a few tricks that we are going to be using here, which may not necessarily be intuitive. Here is the first one, that we know the expectation of x is that, right? And we can easily substitute it, but for now, we are going to keep this here as it is, like that. And you understand very soon why we do that, and to keep the expectation as it is and not substitute it as we did with the variance. The reason why we actually, I can already say why we are substituting the variance is that it's given, plus remember, we want this equation to be also in terms of our beta and alpha, so that we can solve the equation simultaneously. Now, the next step that we take is now to go back to the equation that we had there, what we are equating, which is the expectation of x squared, which we now have in this form, and we write as beta minus alpha squared divided by 12 plus the expectation of x all squared being equal to 1 over n, the summation of our xi squared, like that. And now we get to see the reason why we don't substitute that expectation of x. And the way we would do that is as for, and the reason why is what I'm going to write down now. So now you make this here the subject of the formula. Okay, I'm going to write this here. We'll use this. We had alpha plus beta being equal to 2x bar. So this equation here, what I'm going to do now is to have beta minus alpha squared divided by 12 being equal to 1 over n summation of our xi squared minus the expectation of x like this here, O squared. Okay, cool. And what we are going to do, and this here, again, it's very important to note that you don't always do this, but this is because this expectation of x is not coming from us saying expectation of x is equal to x bar, right? It's not coming from that. And because of that, we can easily now write this as 1 summation of our xi squared minus this here becomes just x bar squared, like that. Okay, that's one of the first tricks that we use there. And I'll quickly just go over it again. We got to this part. I hope that you guys were following because no one mentioned anything. And we got to this part there. And we did not substitute the expectation of x squared. Why? Because what we want is to have it in this kind of a function. And instead of having this as the expectation of x there, we are going to rather express it as an observed expectation, which is just x bar all squared. And straight up from there, what you do, this is a fact, something you would actually prove in 2004 next semester. And this is that 1 over the summation of xi. Note this, this 1 over n is actually just affecting the summation of xi squared and not minus x bar in this case. But this term here can actually be written as 1 over n, right? And you would have 1 over n and the summation of your xi squared minus x bar all squared, now like that. So these are, so far, probably the most important things we have done so far is that we had this term here, we just substituted, and now we brought it this side, and we've written it like this, and this whole term as it is, we have written now written it like this. Something that I'm saying this here is something you will get very used to in 2005 and be proving that. And one of the reasons why I mentioned that this 1 over n is only affecting this part is because in this transformed term that we now have, this 1 over n is actually affecting the summation of everything like that as it is in the brackets like that. So this is something that's very important. And after that point, there will no longer be any funny tricks that we'll be doing. And what we'll have is just that this b minus alpha squared is actually just equal to 12 divided by n, the summation of xi, that's supposed to just be the sum, xi minus x bar all squared. I was supposed to remove that xi there. Sorry about that. Then this is x bar all squared. Therefore, our beta minus alpha is simply equal to the square root of 12 over n, and we have our summation here of xi minus x bar all squared, like that. So yeah, that's quite important. And now we have 2 functions, right? We have 2 equations. This is our other equation, and we also have that alpha plus beta is simply equal to what? 2x bar, which means I can write my alpha being equal to 2x bar minus my beta, like that. So that is an equation that we have. So now what I'm basically just doing is trying to solve simultaneously, right? Which means straight up from there, I will have, in this term here, instead of writing alpha, I'll be substituting there as follows. So that this will be beta minus 2x bar minus beta being equal to the square root, the square root of 12 over n, and our summation of xi minus xi squared, like that. Please allow me to write this term within the radical sign to be star for the sake of space. So whenever I write star, I'm just referring to what's inside the radical sign. So that this here will be beta minus 2x bar plus 2 beta being equal to the square root of star, right? Star, where that star is what I've mentioned to be in the radical sign. And what we simply have, okay, I'm being funny here. This is just plus beta, so that beta plus that beta gives us the 2 beta minus 2x bar being equal to the square root of star, like that, so that our beta, our 2 beta is equal to 2x bar plus the square root of that, and our beta will simply be equal to 2x bar plus the square root of star divided by 2. So this you can even write MME there to show that this is our estimate using our method of moments for approach. And from there, we can now conclude that this alpha, which is equal to that, will now just be alpha MME is equal to 2x bar minus, instead of writing beta, now we write 2x bar plus square root of star divided by 2, which is equal to, then this is 2 here, then I will have, we will have what we have, then this will be, instead of doing that, actually instead, what we can do is to have 2x bar, right? You have a 2x bar minus, I want to break this 2 here, so that I have a 2x bar divided by 2 minus the square root of star divided by 2 again. Now, you could have done it either way from there, but I'm just, you see the reason why I'm doing it this way is because I want us to have 2 bar minus x bar minus the square root of star over 2, so that when we simplify that, this just becomes our alpha MME will just become x bar minus the square root of star divided by 2, which is just equal to 2, and then that becomes 2 bar minus the square root of star, like that. So something that I have not mentioned, which could be given in the formula, in the information, is the fact that your alpha is actually less than your beta, right? Your alpha is less than your beta. This will help in a case where maybe you would have done this through a different approach, maybe using a quadratic formula, and now you have that your answer is actually x bar plus or minus that, and now you want to choose which one is which. But the fact that x alpha is less here, as you can see, this here is the one with the minus, whereas our beta has got plus there. So in my opinion, this is as bad as it gets when you are dealing with estimating your parameters using the method of moment estimate approach, where you actually just have 2 parameters that you need to estimate. Okay, and again, I know there are funny things that could be a bit unsettling here, but these are just, I wouldn't even just call them facts. There are facts that if you can just understand on how we have used them in this approach here, is basically the same way that you use them again, because in any scenario, you'll be given a PDF or a CDF, right? Which you can, from your own calculations, you can find the expectations in any other moment, or it can be given to you, and all you just have to do then is just to follow the same approach. If that's the case that's given there, or it could be as easy as you simply just having to estimate one moment, and then we saw a small example on that, and that was quite easy. We probably might see another example again on that. Cool. And just give me a second. Okay, cool. So before I move on, can I just get some sense of reaction to make sure that you guys are okay with the example that we've just gone through now? Okay, that's the majority. Awesome, cool. So the next thing that I want us to quickly look at is the maximum likelihood approach. Probably the most popular of them is this one here. You will use it more often as you go onwards. And it goes as follows, right? It starts, if you want to find your maximum likelihood estimate, right, you'll be given your density like that. This is just showing that your density and your parameter of interest is that. It's not a conditional PDF. And then you find that the approach involves you finding your likelihood function, which you find by simply taking the product of your density like this. Then the next thing is for you to take the log of that function. That is ln of your likelihood function. then you need to find the first derivative of that, and you equate to 0, and you simply just solve for theta. Again, something that is very simple, just that the function can be a bit messy, and okay, I'll slow down. Sorry about that. Just that I felt like I was going to be behind time, but I'll slow down. So what we're dealing with is now our maximum likelihood estimate, right? And the way we'll do that is you'll be given your density, then you need to find your log likelihood function, which is simply taking a product of your density, right? You'll see when we do an example, it will make much more sense. Then from there, you need to take the log likelihood function of that, right? It's just saying taking ln of what you would have had there. Then after that, you just let your log likelihood function be equal to 0, and you solve for your theta, right? You solve for theta. So I might as well just mention this here while we're here. It could happen that you can have a density which might have 2 parameters, right? So instead of just having a theta, you might have one which is called also a lambda, like that. So when you want the MLE, it means when you get to this point here, when you get your likelihood function, and now you get to this point where you want to take the first derivative. If you want the maximum likelihood estimate for your theta, you will take this here with respect to theta. But if you want the maximum likelihood for lambda, you will take the log likelihood function, you take the derivative with respect to that parameter of interest that you want. So that's the little thing that you need to remember if you want to estimate for theta and your lambda. It also then goes back to similar to the MME method, where after you do this here, you equate to 0, you solve for theta, you also equate to 0, and solve for your lambda. And it could happen that each of them can be a function of the other, and you might then have to solve simultaneously. But then again, that would be simple maths, I will assume, because it's just 2 equations, and then you solve all them simultaneously. Okay, this here is called your score function, right? Because the question can simply just be asking you to find the score function. Just remember that a score function is simply your log likelihood. To first quickly get out of the way analog likelihood functions is the following, because we are still going to come across more functions where we have to take the maximum likelihood estimate, and then we can just simply do that with functions. But what's most important, right, is suppose you are given the function x1 and it goes on to xn, right, and further on you are told that these x's, right, are uniformly distributed between 0 and theta. I don't know if you've noticed yet, but the uniform distribution becomes very popular under this section, whereas in the previous sections, it was mainly the exponential and the gamma, but now the uniform becomes quite important. And the first thing, the question just asking you to find your MLE of your of theta, right? You want the MLE of theta, and we know that firstly, the first step is for us to find the likelihood function. And the likelihood function of theta here will simply be equal to what? The summation, the product from I equal to 1 to n of our PDF, like that, which is simply equal to the product from I equal to 1 to n. This is a uniform distribution, right, between 0 and 1, which means its PDF is simply equal to 1 over the length, right? The length of which we are saying the random variable is uniform on, and we are saying this one is uniform on 0 and theta, like that. So what we are saying is that the PDF will simply be equal to 1 over theta minus 0, which will give us 1 over theta, like that. So that is quite important. Okay. And the next thing that we do is for us then to take the log likelihood function of our statement, right? But before we do that, we can just simply simplify this here. So that this is equal to theta to the power n. Because this is multiplying 1 over theta many times. So instead, we are just going to have 1 over theta to the power n. So that taking the log likelihood function of this will simply be equal to ln of what? 1 over theta to the power n, right? And our maths would tell us that this here, because the theta to the power n is on the denominator, this will simply be equal to what? 2 minus ln theta to the power n, like that, such that this will be equal to n minus n ln theta. Okay, and the next step there involves us having now to find the score function. Our score function, which is denoted by a u like that, is just the first derivative of our log likelihood function with respect to the parameter of interest, which in this case is clearly just our theta. And now taking the derivative of our log likelihood function with respect to theta will now just give us minus n divided by what? By theta. And this step tells us that now the last step it simply involves us taking this first derivative and to equate this to 0 and so, which means we need to take n over theta to be equal to 0, and after that we'll have to solve for our theta. But we will not be able to, as you can see there's nothing that you can really do to solve for that function there. Okay, and now I want to quickly go back to what I was talking about when I spoke about the importance of you looking at your PDF now when you're under this section. One of the reasons why it's very important to look at your CDF, at your PDF. So we're told that X was uniformly distributed between 0 and theta, like that. So the reason why I'm saying this is important is because there is this rule here which says that if the range of your random variable, if the range of X in this case, which is a random variable, is dependent on the parameter of interest, then this happens. That's when this happens here, where you get to a point where you cannot solve for your theta like this here. So already when you're doing a question, this is important for you to do. It's very important that you actually go through the process to see that, okay, you cannot solve for it. But the moment you look at your PDF and actually see that your random variable is actually dependent, its range is dependent on the parameter of interest, it means you are definitely going to go to get to this point. What's more important now is what you will do when you get to that point. And this is what you're always supposed to do. And that is, if your X, right, is greater than the parameter of interest, then your maximum likelihood of your theta will simply be equal to the smallest observation in your data. Then if your X is actually less than your theta, then your maximum likelihood estimate of that will be equal to X of n. I'm going to explain this properly. This is quite something important which you will not find on your formula sheet, but very important for you to know. So what I'm saying here, okay, not really me, I'm just saying what the notes say. What the notes say is that when you are trying to find the maximum likelihood estimate, right, of some function, and you notice that the range of that random variable depends on the parameter. What this means is that if you look at this, this is saying it's uniformly distributed between 0 and theta, like that. Which means if my theta is equal to 2, my function could be somewhere here, maybe to be here. But if my theta is now 10, this range on which is uniform could be somewhere here. So as you can see, my range in this case here is actually dependent on what my parameter of interest is, which is my theta. And once that happens, you will always find yourself in a situation where you will not have, you will not be able to solve for your parameter of interest. In most cases, the way to come across is it being in this manner where you have some function and your parameter of interest is in the denominator and you have a 0 there. And this is what rescues us by telling us that if your X is greater than all the thetas, right, then that's what happens. But if your X is less than that, I want to explain this here because our answer in this case is that our theta, the MLE of our theta in this case is the largest observation. Why? Because this second statement is saying you've got a number line like this here, right? And this is uniformly distributed between what? 0 and my theta. So it means I've got numbers here, my x's, my x's that are moving, the small x's that I have there, my x1, x2, I've got small numbers that are in between here, and they are all uniformly distributed where between 0 and theta, right? And in this case, as you can see, all these x's are here, meaning they are less than this theta, the parameter of interest. So all the x's, as you can see, the x is less than the theta in the sense that all the numbers that you have here, the x's will all be below the theta. And once that happens, then your MLE will simply be the largest observation in your data that you have. So in a case where you find that all your x's are actually greater than your theta, that is, you might have your theta being somewhere here and something else, maybe not even a bound. You will see the next example that we are going to do actually. Actually, not. Let me not explain this statement now. I'll explain it with the example that we are going to do. It just makes everything make more sense. But I just hope you understand what I've done here. The fact that our range here is dependent on our parameter of interest, and this rule tells us that since your x's are all less than this parameter theta, your MLE will simply be the largest observation in your data. So in a case where you're actually given data points like that, you can go on further to say, therefore the MLE estimate will be equal to what? To 5 in that case. Which brings me to something before we go to our next example. There are questions which could actually ask you to find the maximum likelihood estimator, all right? Estimator and the maximum likelihood estimate. Right? There is a difference between the two in the sense that the estimator will always be a function. This is a function. This will always be a function, right? In theta being equal to 2x bar over n. This is an estimator. An estimate will require you going to your data, finding what this mean is, and finding what that n is, and actually substituting them there. And that is actually a numerical value. A numerical value. And the reason why now this quickly came to my mind is because in a case where you are just asked to find the maximum likelihood estimator, you can simply end at this point here, like that. But in a case where they actually ask you to find the maximum likelihood estimate, and you're given the data, then you can go as far as you now trying to locate what is that largest observation in my data, and you plug it in. So just want to put it out there. When you say estimator, leave it as a function, and estimate, you leave that as a numerical value. So the next statement, which I just want to quickly look, the next example, which I want to quickly look at to show the other side of the coin where your x is actually greater than all your thetas, is an example where your PDF here is given as follows. You're given your PDF to be equal to E minus X minus theta, like that. Then you are told that X is greater or equal than theta. Again, the whole thing about make sure you quickly look at your PDF properly before you go further. As you can see here, we are given our PDF as normal as we've been doing, and now we're just paying more attention to the fact that they are telling us that our x's are greater than all our thetas, right? So given that your x is greater than theta, in some PDFs, usually like your exponential, you have this extra term which says x is greater than 0. That is fine. You would find your MLE in a normal way, and you will be able to find your answer, because the difference between these two, this is saying that this is my 0, and my x values are all going that way. Whereas this one here is saying this is the theta and all the x values are going that way. But if this theta is 1, is 0, it could also be there. But if my theta was 1, it could have been there. If my theta was 2, it could have been there, going onwards like that, right? Which definitely now shows us that this range of our x here, this range of our x is dependent on what? On our parameter, which is theta, which means that when we find our log likelihood function, our likelihood function first is the product from I equal to 1 to n of E minus X minus theta, like that, right? Which then we can remove this product sign and make that into a summation, because this is like saying e to the power x times e to the power x times e to the power x, which is just equal to e to the power x plus x, right? And this, okay, I know I'm just explaining something you already know now. So this is the e to n of our x minus theta, like that. Now the next step is for me to distribute this summation sign, right? Before I even go there, let's take our log likelihood function, which is simply just going to be ln of e to the power minus I equal to 1 to n of our x minus theta, like that. Okay. Then the next thing that we do from there is the fact that we're going to drop this down such that our log likelihood function will be equal to minus the summation from I equal to 1 to n of xi minus theta, like that. Okay, this is something that I always forget to write the xi's, right? I always just write x. I don't think we'll penalize you for that, but because this summation is actually saying you're running from I to n, you need to show what's actually moving from I to n, and it's your xi's, like that. So yeah. Then this here will be equal to, you can now distribute this summation sign such that this is the negative summation from I to 1 to n of your xi, then that and that will become positive, so this theta, so that becomes plus the summation I equal to 1 to n of my theta, which this is just my summation from I equal to 1 to n of xi, but this becomes n theta. Why? Because nothing is really dependent on n there. On I, there's no anything with an I subscript, so it's just like theta plus theta n times, which is the same thing there. So the next step there, the next step that follows is for us to find the score function. By score function, I mean it's the first derivative of the log likelihood function, which is this here, which is our score function, and this is just a matter of us taking the derivative with respect to our derivative with respect to the parameter of interest, which is theta, right? And that will just give us a what? An n, like that. We get an n, and we have to let that be equal to 0. And it's just a matter of saying n, okay, no, something, oh yeah, before we even go further, the fact that our score function here is just n, like that, but we do not have our parameter of interest, because remember the reason why we do this here is to try and estimate our parameter of interest, which means whatever function we get as our score function should be something in terms of our parameter function, so that when we equate that to 0, we can now actually get something in terms of our parameter of interest. So already, this is something we expected. It means once you get to this point here, you can't solve there, right? Which means we have to turn back to what we had mentioned here, because remember, just as I've ramped this here, we had our PDF and our condition that our x is greater than theta. And the fact that x is greater than theta, we've already established that this means our range of x is dependent on the parameter of interest, which means that we then turn to these two and determine which one is which, and as it is, this here will correspond with that, which means I will have my theta somewhere here, and my number line is going all the way here, and all our x's are going towards infinity, like that, or rather maybe just some n that we don't know. And the fact that this our x is greater than all the parameters, we can now conclude that therefore our maximum likelihood estimate here will simply be equal to xi. That is the smallest observation that we have. Again, differentiating between an estimator, this is our maximum likelihood estimator, because again, this is still just a function telling you that it's representing as the smallest observation in your data. But if the question was asking you for a maximum value, and you have your maximum likelihood estimate being equal to that value. Cool. Okay, so there's a question which is asking if we have to go through the whole process. Yes, you would have to go through the process, because this whole thing about being dependent on your day, on your range, and thus you can't solve. Yes, it is in theory. That's what it says. But the next thing, the reason why you have to go through the whole process again is to actually show that, okay, as much as we know that once your range is dependent on your parameter of interest, you cannot solve. That's what we know in theory. And then you actually like put it down there when writing, okay, and it shows that you cannot solve there. Then now you can start applying this. So yeah, you actually need to do that, because one of the reasons when you're trying to estimate a maximum likelihood, right, as you saw in the procedure, there will be marks for you finding your likelihood function, even your log likelihood function, and especially your score function, because the score function is always very important. Why? Because whenever you have okay, in this case here, it doesn't really help that much, but okay, I should not go there. We'll get, okay, let me mention it. Whenever you have your maximum likelihood estimate, you need to check if it's a maximum or not by finding the second derivative of your log likelihood function, right? Your second derivative, that is this here. But again, what I'm saying now, it doesn't really help with what we're doing here. The question was whether we have to go through the whole process here, and the answer is yes, you have to go through the process, because what we are saying, what we are doing here is what it says in theory that you will not be able to solve, but you still just want to show that, okay, you cannot solve, therefore I'm turning to what the theory says I should do, and you end up having your answer like that today. Okay, I hope that answers the question. Cool. The next thing that I want us to look at, so again, it goes back to, I think I've mentioned this before, that a discrete case is probably one of the easiest cases that we have, but the problem is that we focus much more on the continuous case, such that, give me a second, we focus more on the discrete case, such that when you get a question like this, which is giving you a PMF of x, right, being equal to p to the power 3 and 1 minus p squared and 1 minus p all squared and 2p 1 minus p, right, and x is equal to 0, x is equal to 1 here, x is equal to 2, and then x is equal to 3, like that. Then it even goes as far as giving you, give me a second. Oh, okay, cool. There's a question there which is asking how you would find the numerical value of this year, right? In that case where I said if the question is asking you to find the maximum likelihood estimate, like this year it can only be found, actually an estimate, a maximum likelihood estimate can only be found if they have given you the data. So for you to find that numerical value for this year, it means they gave you data, they gave you 2, they gave you 3, they gave you 1, and they gave you 5 and a 4, right? Firstly, you have to order your data in ascending order, 1, 2, 3, 4, and a 5, right? And once you do that, this is saying the smallest observation in your data, and thus you can conclude that your MLE, in this case here, your maximum likelihood estimate, this estimate, the numerical value of x1, is just that you'll be given the data and you just have to find what the smallest observation in that case is. Similarly, if your MLE is xn, the same thing where you say your MLE estimate in this case will be equal to 5. It's only in the cases where you're given a function 2x over 2n, where you actually then have to do some calculations and add up this to find your mean x bar, like that. Cool. I hope that answers the question. So what I was saying now is that we are given. Let's see. There's a question there. Oh, okay. Okay, let's just try to give it one more try, and if it does it again, just let me know. Then I can get someone to try and check it out for us from one. Cool. So I was saying, in a question where, if we get a question where you're given a PMF like that, and you are told that your N is equal to 150, right? And it goes on further to tell you the number of times that each event is occurring. For example, that your 0, that x is equal to 0 occurs 24 times, okay, 24 occurs 24 times, and then that x is equal to 1 occurs 54 times, and that is 2 occurs 32 times, and your 3 occurs 40 times, like that, okay? Then the question asks you to find the maximum likelihood estimate of P, like that. Actually, in this case, let's rather say the maximum likelihood estimate yes, of P. And we know already that for maximum likelihood estimate, we first find the likelihood function, the likelihood function of P, right? Because what we want here is the maximum likelihood estimate of P. That's what the question needs. So we start this by finding the likelihood function, which we know is found by simply taking a product from I to, which is 1 to n of our PMF in this case, right? And the interesting thing about this function, the discrete case of the PMF, is that instead of us, it's still the same thing, but the way you then do this is to simply let this be equal to, you take the PMF there, p to the power 3 when x is equal to 0, and you are going to power this to the number of times that x becomes 0, which we know is equal to 24. We go on further to take the next part, which is 1 minus p multiplied by p squared, and you're going to power this here to the number of times that x is actually equal to 1, which in this case we find that is equal to, that is 54. Then you go further to have 1 minus p squared, and this only occurs how many times? 32 times. You multiply this by 2p, 1 minus p, and this is all to the power what? 40, like that. Okay, so that's what you simply just do in a discrete case like this, where you're given a PMF, that is the probabilities, with when like the probability of x and the value x and its probability. For you to find the likelihood function, all you simply have to do is to take that p, that probability at that point, and you x is equal to 1. Okay, hope that makes sense. Then the next thing that we do is now to, this is equal to, now you consider the p's, right? But as you can see, we can start with the number. We have a 2 here. I don't know if you can see properly, but in our function, we have this last term all to the power 40. Why? Because this is happening 40 times. So what I'm going to do is to take that 2 out, and then I'll have 2 to the power 40 here. Well, this 40 is going to be distributed to every term that's inside here. Then the next thing that I will do is to take my p's. So you see that we have p to the power 3 to the power 24 here, which is simply just p to the power 3 times 24. We also have this other p to the power 2 inside the bracket being to the power 54, which is simply just equal to 54 times 2, right? Simply p to the power 54 times 2. We also have a p here, which is simply just equal to p to the power 40. So when you add that 24, the 54, and the 40 there, you would find you would end up having p to the power 220. You do the same thing for 1 minus p. We have a 1 minus p to the power 54 here, 1 minus p squared to the power 32, and a 1 minus p to the power 40. You take your 1 minus p, and you're going to add what all that is equal to, and you'll find that this is equal to 158. So this is your likelihood function. We go on further to find our log likelihood function, which we know is simply equal to ln of what? Your log likelihood function, which in this case is 2 to the power 40, p to the power 220, 1 minus p, all to the power 158, like that, right? Which we know now mathematically is equal to ln of 240 plus ln of p 220 plus ln of 1 minus p, all to the power 158, right? And straight up from there, we are going to go on further and simplify this mathematically, so that we have 40 multiplied by ln 2 plus 220 multiplied by ln p plus 158 multiplied by 1 minus, multiplied by ln 1 minus p. Cool. Guys, are you following? Can I just get a reaction to make sure that we're together? Awesome, cool. So that's what we have now there as our PDF, as our likelihood function, or actually our log likelihood function. Then the next thing that is important is for us to get our score function, which is just the first derivative of our log likelihood function with respect to the parameter of interest, which is p, like that. Okay, so what we then do from there is to take the derivative with respect to p, and we get that this here is equal to 220 divided by p. So this one we ignore it because it's just constant, and now I've taken the first derivative with respect to P of that term, then I'll go on further to also take the first derivative with respect to the other term, which we will find as being minus 158 divided by 1 minus P, like that. So it was just plus 158 divided by that, multiplied by minus 1, which would get there. And then the next thing that we have to do, as by the procedure, is to let this be equal to 0. Why? So that we can now substitute, solve and have a formula being equal to 158 over 1 minus P. And all we just have to do here is to solve for P by making it the subject of the formula. And if you work around with this, you would find that you would end up having that your P, which is the maximum likelihood estimate, in this case, is simply just equal to 220 divided by 378, which you get as 0.582. Okay, I'll quickly just talk for a second here. So what we've done, we're given our PMF, we found our log likelihood function here by simply multiplying marginal probabilities by the number of occurrences that is happening, right? And then we got our likelihood function, we got our log likelihood function by taking the ln of that. Then we went on to find our score function, which is simply just the first derivative of our likelihood function with respect to the parameter of interest. And then now that's what we got. And we let our log likelihood function, the first derivative of that, be equal to 0, right? Which then gave us that our P was equal to that term that I've written there on the board. And I'm just looking off. So now that we have our maximum likelihood estimate of P there. Cool. Then the next term is what I want us to discuss, right? I just thought that was the best way to actually introduce this whole concept I'm going to discuss now. So the next term, this is exactly like a kind of question you could expect in a test where you found the maximum likelihood estimate. Then the next question would ask you to find a 95% confidence interval, and they like even including a distribution free here, which means you will need to use your asymptotic variance. You will need to use your asymptotic variance in this case here, okay? Which we know, okay, let me say we know, but I'm going to write that down now, that our asymptotic variance, right, will be given as follows. So in general, your confidence interval for some parameter beta will be beta plus or minus 1.96, right? Assuming it's a 95% confidence interval divided by the variance of that P, of that beta, like that. So in this case here, it will be our beta, our P, right? Our maximum likelihood that we have there, plus or minus 1.96 and its variance. So then what we need to do is to find the variance of beta, the asymptotic variance of beta, which in this case means we need to find the asymptotic variance of P, like that. And then the formula for an asymptotic variance is given as being 1 over, it's just given as being 1 over n, I'll write a P here because we are dealing with P, but a general formula for this, for asymptotic variance, is simply just equal to 1 over this here theta, right? For some parameter theta. So what you do next from there, this part here, very important, is equal to minus the expectation. I always write this x here, just to remind you that when you actually find this expectation of the second derivative of your log likelihood function, right, you remember that if there is an x here or any random variable within that function, you need to remember that this expectation should actually affect that random variable there. You will see what I mean exactly, but it's just important. It's important for you to actually always remember that this is the expectation of some x, but with that function that you have in the function. Cool. And the next thing that you have to do, also very important, which I mentioned earlier on, that in most cases you would already have what this is here, right? Because this here, this is maximizing, right? And when you get an answer, it's always important, right, for you to find the second derivative of your log likelihood function. And if it's less than 0, then what you had there is a maximum. So this is very important. Something I always forget, but it's important probably with the mark, depending on who your marker is. But whenever you find a maximum likelihood estimate, when you are done, take the second derivative, second derivative, and then show that it's less than 0, which then proves that what you actually have there is an estimate, because it is the maximum, because it could be, because you're maximized, it could be a minimum, but for you to show that it's a maximum, this has to be less than 0. And again, it's not a waste of time, because as you are going to see now, we are still going to use that second derivative of your log likelihood function now. And we use it as follows. Cool. So what we now have is that we want the confidence interval, right? A confidence interval for our parameter P, and this requires us to find the asymptotic variance of our P, which we said is 1 over n that, and we said this here is simply equal to the negative expectation of the second derivative of our log likelihood function, like that. Cool. And we remember we had our score function, the first derivative being equal to 220 divided by P minus 158 over 1 minus P. So this now here is just taking another derivative of that with respect to the parameter of interest, which is P, which when you do that, you'll find that your answer is equal to minus 220 divided by P squared minus 158 over 1 minus P, like that. Which this here, if I were to take the minus out, is simply just minus 220 divided by P squared plus 1, plus, okay, to be a minus here, and, plus 158 over 1 minus P squared, like that. And the reason why I did that is for a case where you want to show that this is actually less than 0, right? Because remember, we already know what P is. We know what our P is already. So you can even go as far as substituting that to find that the answer you're going to get here, and then the negative of it is going to be less than 0. Hence, the P that we have there is a maximum, You would write like that. But at this point, that's not exactly what we are very much interested in. What we want to do is to take the negative expectation of this function that we have now. So we want to take the negative expectation of that, because we're in a process of trying to find what the asymptotic variance of this estimate that we have is. So this means we are going to take the negative expectation of minus 220 over P squared minus 158 over 1 minus P squared. Now you will notice that in this function here, there is nothing which has got the random variable in it. So in a way, these are all just constants that we have here. These are all constants. It's like taking the expectation, of A plus B, which we know is just equal to A plus B, right? The only thing that's going to change is that they will be affected by this negative sign here, such that this negative times negative will give us 220 divided by P squared. Then that will give us a plus 158 over 1 minus P squared, right? And remember, we already have our P. What's our P? We want the confidence interval, and you are given the data. Okay, just let's hold on, let's see. Okay, let's just give me a second. Let's try. I'll try and see if I can contact someone. Okay, cool, no problem. I'll quickly go over that. The part on the left side of the board. Okay, cool. So what I basically did, I'm just going to try and I'm going to assume everyone else can see now, those that were frozen. Cool. So where we were, what we did is that we're trying to find the asymptotic variance of the parameter p, and we found the second derivative of our log likelihood function as being that, and we went as far as trying to I factor this negative out so that we can see that it's less than 0 and hence a maximum. And now we're taking the negative expectation of this function here because that's the requirement for us to, this function here is basically equal to the negative expectation of this function that we have there, right? So that's what we basically did. We substituted that function in that there. And the next thing was, what I did was just to point out the fact that because I put this extent to remind you that if there is a random variable in there, you actually need to find the expectation of that random variable at that specific point where you find it in the function, as you'll see very soon. Then what's important is that these are all just constants, so you treat them as you treat the expectation of a plus b, which is just a plus b. The only difference that in this case here, there's a negative there, so it's going to affect this negative and that negative, hence we've got a positive here, that and that as well, hence we've got a positive. So this is what you end up having, right? But we've already estimated what p was, so you then substitute this here, which is 0.582. You then take that estimate you had and you plug it in there so that you have a value, and you would get that this function, this term here, will give us 3714.432, right? And remember, just a reminder, this function is actually just n that p, right? And we know that our variance is actually 1 over that. So our variance of our p, the variance of this p is simply just equal to 1 over this 3714.432. And this gives us a variance of 0.000269. Okay, and I will not look at the variance right now, but what's important is that for you now to get to what your variance is, it's just your confidence interval. I mean, it's just a matter of substituting, because now we have our p, we have the parameter p, and now we also have the variance and the 95% confidence interval, which means we have our 1.96. So our confidence interval will just be the value of p. You have to substitute the value of p. Remember, this is 0.582 plus or minus 1.96 because it's a 95% confidence interval. Then you divide this here by 1 over n that, right? And that's just being fancy because this here is by definition just the of our p like that, which is given as that. So you actually end up getting a confidence interval with numbers. Cool. Then the next part of the question, which I just want to quickly discuss before I get into part C of this question, is the following. That so what we've been doing here, we are assuming we're given this data that we are given, and we found the maximum likelihood as we did. We even found an asymptotic variance and a 95% confidence, a distribution-free 95% confidence interval. Yes, that. And then the next thing is that suppose, right? I say suppose, this is just some notes, right? Not the part of the question exactly. Suppose that now we have a new parameter. We have a new parameter, and let's call that phi. And this phi is actually in terms of theta, right? So this, again, let's say initially we were dealing, let's forget about our example for now. Let's say we've been dealing with CDF with this parameter theta, and we even found the MLE of that theta and everything. Everything we've done for the question we were doing previously, the example, we suppose that we did that for some function, for some PDF with theta, and now we are told there's a new parameter phi, but that same parameter is still in terms of the old parameter that we were dealing with. So this approach now could ask you, the question could ask you, what's the MLE of the new one, the MLE of this new parameter here? This will simply just be equal to that function that you're given there, except that now you're going to put a hat like that there. What this simply means is that if you already have the MLE of what you've been dealing with there, you are going to take that function as it is, and you're going to plug in that MLE like that, okay? Meaning that in that case where we were dealing with P, This year, if it's an h of p like that, you are simply just going to now substitute our 0.582 like that. Okay. Then the next thing, which is very important now, is the delta method. We'll put this into practice soon, don't worry. And our delta method will tell us the following: that okay, this is our delta, the delta method. And the delta method tells us that the variance of the new MLE that you have here is simply equal to what? The first derivative of this function here, this function, the h of theta squared multiplied by the variance of theta, like that. Okay, so just to get this straight now, just to quickly summarize it before we do an example, right? So what this does is that you're given this this data that you're given, right? With parameter of interest is theta. You've done everything that's important that you feel is important there, including finding the maximum likelihood estimate of your theta, like that. So that's what you've done, all right? And the next thing, you suppose you've got new data. Actually, suppose you've got new data, and you even have a new MLE like that, which is, we call it phi. You have a new MLE, I'll write it here, a new MLE, which is phi. But you find that now that this phi is simply just in terms of that parameter that you're dealing with there. So instead of you redoing all the calculations that you did there, it tells you that if you've got new data and this parameter of interest is in terms of the parameter of interest of the data that you've been dealing with, you can simply then find this MLE of the new you should have gotten for your previous data, like that. Theta head. Cool. Then the next thing that we do, cool. Then the next thing that you do, that we're told here now with the delta method, is about the variance, right? To say already, you're given this new parameter and you've got your h of theta, okay? Your h of theta like that, and you want the variance of phi, right? This is quite important what I want to talk about here, because there are some cases which are a bit confusing. So the delta method, right? As much as we're looking at a new parameter now, the delta method does not really, you will see when you do your past test 2019, you will see what I'm talking about. It does not necessarily just refer to a new parameter, but the delta method just says if you want the variance of a parameter, it just so happens that in this case here, we're looking at the variance of the new parameter. This is simply equal to h, the first derivative of h of theta to the power that squared. I'm just repeating what I've written already, and then that, right? My point being is that you can actually be going through a question and you find that your MLE is maybe beta is equal to x bar over 3, like that. This is your MLE. Without talking about any new data, or anything, you can actually just be asked to use the delta method. Suppose use the delta method to find the variance of beta, like that. So again, what this is saying is that what I wanted to emphasize is that the delta method is not necessarily for saying you find the variance of a new parameter, but you can literally be asked to find the variance of any parameter using the delta method. But it just so happens that most of the time we use it to find the variance of a new parameter. So this year you can find this variance using that. In the same way, it was the same way we could have just found the variance of beta by finding the variance of this, right? But now you're also using the delta method, which we say is approximately, in this case here, where your beta is equal to x bar over 3. This means my h function now will be h of x bar. This is one of the things I wanted to emphasize on, okay? It will be h of x bar. And the reason is because this is my beta, my parameter, but it's given in this function there. And your h the input you're going to put in your H there will be the statistic or a parameter which you will find on this side of the function. Okay, you will see what I mean when we go back to our function quickly. But what I wanted to emphasize is the fact that you can use this delta method to find the variance of any parameter. If they specifically tell you, then use the delta method to find the variance of that, which in this case, the reason I wrote this will be approximately the first derivative of h of x bar, and you square that, and this here will be the square root of x bar as well. Why? Because the delta method, as you see here, it says h of theta all squared multiplied by the variance of the theta as well. Just that this theta here, in this case, is an MLE, but yeah, even here, you also, when you get the function at the end, you also substitute with your MLE. I understand that right now, this could just be, it could just feel like a lot of words being thrown at you. So what I'm going to do is to quickly continue, and I'll explain it again. I'm not leaving it, I'm explaining it, but now I'm going to be explaining it with a practical example where we're still dealing with that same question, and part C, in this case, introduces a new function and says that, suppose now there's a theta being equal to P over 1 minus P. So I'm going to do this here on two balls. This side, I'm going to be dealing with our question. Then here, I'll be writing the theory we use to answer this question. So we've been dealing with data with our parameter of interest being P, right? But now we are told that theta is equal to P over 1 minus P, okay? Now, the first part of the question could ask you to find the MLE of this new parameter, right? Which is theta in this case. The MLE of theta, like that. And already we know if you've been dealing with theta, we introduce a new parameter in terms of theta, then the MLE of this new parameter will simply be equal to h of theta, but you're going to do that there, meaning you'll be substituting the MLE of that you already got. So in this case, this MLE is simply equal to P over that 1 minus that, and you know what P your MLE already is for that, it's 0.582. So then you're just going to simply substitute that, and you get something along the lines of 1.372, like that. Okay, I hope that makes sense. So all I've just done is that we are given a new parameter in terms. So let me quickly write that now, that we're given theta and is equal to P over 1 minus P. And when I write this as a function, I would write this as h of P. Okay, h of P, because I know we used in theory h of theta, and one can easily be, you can easily feel like writing h of theta, but the reason why we write h of theta here is because this is saying this new parameter is given as a function of theta, right? So whatever that you have here has got a theta in it, hence we say h of theta. The same way we've got P 1 minus P here, and we have h of what? Of P. And that is the reason why when we had when that example was given and we had x bar over 3, we would end up having what? Our h of x bar, like that. For the same reason that there's a P there, so we would also have an h of P and an x bar, like that. So I hope that is fine. Then part D will ask you to find now the variance of P. The variance, part B will be asking for the variance of this parameter of interest P, like that. Okay? And not P, man. The parameter, the variance of this theta that we have. So we want the variance, and by the delta method, we know the delta method tells us that this variance will simply, the variance of our theta in this case here, right? The reason why I really want to stress this out is because you can easily go back using the formula to use the formula where you're going to write is equal to h of theta all squared and whatnot. This here will be wrong. This is just the general formula, but in this case, to be specific, this here, remember our theta is in terms of P, so it means this will be h of P, the first derivative of our h of P all squared multiplied by the variance of that P there, like that. Okay, that's what I just really want to stress out there. And then because this is something that can be easy maths, but sometimes can become a little bit confusing. And you would find that your first derivative, actually, if you take the first, because our h of P in this case here is equal to P over 1 minus p. If you take this first derivative like that, this will simply just give you something along the lines of 1 minus p all squared, like that. Which means the variance that we are talking about will simply be equal to that 1 over 1 minus p all squared, and you square this again, multiplied by that 0.00269 that we got as being the variance of p. Okay. Like now, I would. This is one of those times when I would really like your reaction, just to see how things are. How does it seem from your side there? Is it okay? Awesome. Cool. All right, and the others, I just want to make sure that no one is frozen and being left behind. There are 2 that haven't replied. Awesome, cool. Let me just quickly check the time so that maybe we can, we'll have a small break at some point. Okay, so let's ask, okay, I want us to quickly look at, all right, I want us to quickly look at this one example here, and then we're going to actually just discuss it, and then we can take a small break at 7 exactly. So this question here, it's just again to emphasize, because I understand there are other methods that we've been looked at, like the method of matching quantiles and the list of squares, but those ones are very easy, and there's only just the reason why they're even there most of the times, they'll just come so that they give you a theta being equal to some function. Then once you have that, they'll start asking you questions about maybe your delta method and stuff. So instead of saying you've got a u parameter theta equal to p minus y minus p, they'll ask you to find your MME estimate. Then when they're done, then you're asked to find the variance of that using the delta method in a way. But anyway, most of them they're not important, but we'll quickly look at them. What I wanted to emphasize on, so just trying to see if it's very important. Okay, it actually is important. What I wanted to emphasize on, I'm just going to discuss this question. I'm not going to go through all of it. You've got your y1, you've got a y2, O until yn, and this is IID, right? You are told your y is with an exponential distribution with lambda equal to 1 over I alpha, like that. Then the first question will ask you to find the maximum likelihood estimate. By now, we know that this is just from I equal to 1 to n of your f of y, like that, which you can just find using the information that you have there. And you will go through the long process that we know for MLE to finally find that your maximum likelihood estimator will be equal to the summation of your yi over I over n. Again, in this question here, in case when you try to find the MLE there, you'll find that your answer would actually just be the summation of your yi over in, right? This is correct because it's the same thing as we have here, okay? Because you are just going to have that here multiplied by 1 over n, and you get the same answer. So do not worry about that. Then the next part of the question was actually just asking you to show that the distribution of this here actually is a gamma distribution with n and alpha over n, like that. It's just a question of using MGFs and whatnot again. But what I wanted us to get to, what I wanted us to get to, which is my point of interest, is we know that the variance, Can you hear me now? Awesome, cool. All right, cool. So yeah, let's continue. What I wanted to go through, okay, I don't know how I had done that. Somehow I had actually muted myself. So what I want us to look through is that in this kind of a question, I remember when I was talking about the importance of writing this X here, right? That's what I just want us to look at. And papers are mixed up now. And okay, we wanted to find the asymptotic variance of our MLE, right? And I'm saying that in this question, the MLE had been found to be this here, and which is exactly the same thing as that. But you'll see the reason why it's important to either write them in the other way, to write them in this way to be specific. Okay. So the next thing that we do here is okay, we want the asymptotic variance, which requires us taking the negative expectation of that. In this function, we would have found that our score function is equal to minus n over alpha plus the summation of our yi over I alpha squared. We can go on further to take the other derivative again to find that this here was equal to n over alpha squared minus 2 the summation of our yi over I to the power 3, like that. You can go on further to find that that is the case. And now it goes back to the reason why we write this function in that manner there, in the sense that, okay, I'll quickly write it first. I'll write it down the way I'm talking about, and you can see what I mean. So instead of writing our second derivative of our likelihood function like that, I'll write this here as being n over alpha squared minus 2, the summation of yi over I, all divided by alpha to the power 3. Again, it's the same thing in the sense that if I were to multiply, to take this here and divide by 1 over alpha 3, I will get back to the same question to the same expression that we had there. Okay, and the reason why, okay, no, it's fine, I'll get there just now. And the next thing that we do is that we have this function, which is what we are trying to find, the negative expectation of this function that we have there. And in this case here, this would be equal to the negative expectation, but I will write a y here because we're dealing with the random variable y and not x. Then we would have n over alpha squared minus 2, the summation of yi over I divided by alpha to the power 3, like that, okay? And in the information, remember, we had that our y was exponentially distributed with lambda equal to 1 over I alpha, like that. And the reason why I was trying to emphasize the point where I always try to put that there is that you will not always have variable, and that could make a difference, which in this case, this will be equal to the negative expectation of y, but what I have here will be the n will not be affected with the constant, so we have minus n over alpha squared, then we're going to have plus 2, the expectation or the summation of the expectation of yi divided by I, or divided by alpha 3, like that. Okay. Please do let me know if maybe someone's screen froze and you want me to recap on something quickly. Well, I think even mine was frozen for a second. Oh, is everyone okay? Can I just get a reaction? Is everyone okay? I've got everything on the board now. Cool, awesome, cool. Let's continue. So what I've done here was just to show that we need to take the negative expectation of that. But in this case here, unlike the cases we've seen so far, this is not a constant. Okay. There is a question. I just saw a reaction which was like clapping. Was that like a go ahead or is that like a stop? Okay, cool. So, okay, so no problem. So what the reason why I am doing, I took this example is because it's important to always remember that this here will not always be just what's in the bracket. In most cases, it does seem like it. Why? Because you have constants. But in this case, as you've seen, this in expectation, this came out as a constant, the 2, but then the expectation actually goes to our y there, which we know our y is with an exponential distribution with lambda equal to 1 over I times alpha, which means the expectation of y is actually equal to 1 over I alpha, which we can all agree is equal to I alpha, right? Because remember, the expectation of an exponential distribution is equal to 1 over lambda. So to continue from there, you would find that this here actually just becomes minus n over alpha squared plus 2, the summation of I equal to 1 to n. The expectation will become what? We said I alpha, right? And then we have this divided by I and O divided by I to the alpha to the power 3, like that. So our i's will cancel, the I will cancel there, so that you have minus n over alpha squared plus, now this is just an n, so this will be 2n alpha divided by alpha to the power 3, so that the alphas will cancel, then we'll be left with 2 here, and we have minus n over alpha squared plus 2n over alpha squared, like that, which this here is just n over alpha. Right, I hope that makes sense because it's minus that over alpha squared plus 2n over alpha squared. So we will take a common denominator and just say 2n minus n, and we get our answer to be n over 2. But remember, what we wanted was the variance of that, right? What you said was 1 over this function that we have here, which we're trying to find, and we found is n over alpha. And when you when you simplify this here, because it's 1 over this function, it should simply just be equal to alpha over n. That is our variance of that function there. So it means this is our asymptotic variance. So it means if you want to final confidence interval. And one last thing before we take a break is if you were then asked to find the MLE, if you were asked to find the MLE of theta being equal to, let's say, alpha squared, all right? It goes back to that, it goes back to what we've been talking about. If you are given a new parameter, but still, oh yes, no, it's alpha squared, alpha squared. Thank you for that. This is alpha squared because we had n over alpha squared there. Thank you very much for that. Because alpha squared like that. Thank you. So the next part of the question could be asking you for the MLE of a new parameter, but this here is also in terms of what? Of our alpha, like that. So it just means that the MLE for this new parameter will simply be equal to this here, and you have that. So it's just equal to that squared, that. Okay, so yeah, you can actually even just leave this question there as it is because we don't have any numbers that which even if you substitute the MLE for that, you will simplify into being one numerical number. So you're welcome to even just leave like that. So this means you can even be asked to find the variance of that using the variance of this here, using the delta method, and this will just be a matter of you taking the first derivative of this here, right? And you square that, multiply it by the variance of that, which we have this variance already, and we have this function of theta being just equal to that. You just take the first derivative of that, you square that, and you multiply with what we have there, and you will get your variance using your delta method. Okay, cool. So, yeah, I think we can just take a short break. Then when we come back, we'll try to quickly go as fast as possible on the next material. So it's like a 5-minute break. Let's try to be back at 6 minutes past 7. 6 minutes past 7. Okay, cool, guys. I'm going to assume that you guys are all back so that we can continue. And the first thing that I want to outline. Okay, so what I want us to first look at, like there's a question in the group there which was asking where we got the fact what could actually be asking what the distribution of this is, or maybe show that it's got a gamma distribution with the parameters that I wrote down there earlier on, where the best way for you to do that was just to use your MGFs, right? Because remember, to show that this has got a gamma distribution, all you have to do is to find the MGF of this here, which you can find, you can show is similar to the MGF of a gamma distribution in that case. And that would be quite not that difficult because it's got a Y here already. So it's just a matter of using the definition of your gamma distribution, and you go on further like that to find your MGF of your alpha like that. That's how we got that. Okay, but again, it's a question which was like show that this distribution. So meaning that in a case where this whatever we did there could have actually just been done because the distribution was in a way then given in that question there. Cool. I hope that answers the question. What I want us to now look at while we race against time now is we're going to start with the method of least squares, right? There's not much that's left. That's the method of least squares. Was the most stuff which is important, the MME and your maximum likelihood estimate. That's where most of the questions actually come from. You're finding the estimates themselves, you're finding your asymptotic variance, the confidence intervals, you're being able to use the delta method to find your variance, and also just finding the variance of a new parameter, which would be in terms of the older parameter. So now we are going to quickly look at the method. We're going to look at the method of least squares. Method of least squares, and the aim of this method here is again just to maximize. We want to maximize, right? We want to maximize the function q is equal to the summation of xi minus the expectation of xi, and we square all of this here. Okay, so this is another method for us to estimate the parameters of a random of a distribution, and we call this the method of least squares. And what you want to do is to simply get, okay, the first thing you do is to get this function here, q, right? And q is simply the summation of the expectation of the difference between xi and its expectation, and you square that. And once you do that, to maximize it, we're going to take the first derivative of this q and you let that equal to 0. Then after that, you just have to solve for I will write theta. I'm going to assume our parameter here is theta. So you solve for your theta. So in most of the cases, again, in this question here, most of your work that you're going to be doing is to be finding the expectation of your xi. This can be you can be given a function which you can find on your formula sheet, and thus it's much easier for you to find the expectation since it will also be given there. Or in most cases, you will actually have to calculate this here manually, and that's actually most of the work you'll be doing in this question. Then after that, all you have to do is to maximize this function q, which, like I mentioned, is taking the first derivative. And once you have the first derivative, you simply after that you simply just say that equal to 0 and you solve, right? So suppose, just to show what I'm saying in writing, suppose you are given f of x like this here being equal to 1 minus theta x minus So we are given this density, right? And we are saying what we want is our aim is to maximize this function Q. Actually, you put a negative there. It's supposed to be, yeah. Okay, let's say it like that. We want to maximize that function, and then what we do from here, we're given our density. Again, this is just something worth mentioning, not for this question, but again, just to remind you that look at the PDF correctly, and as you can see here, it's defined as our x being between 0 and 1. So now we are sure that that there is not dependent on the parameter of interest. So in a case where we're supposed to find an MLE, we would actually be able to solve what it is, right? Then the next thing that we do is to find the expectation of x. Why are we finding the expectation of x? Because we want to find the function q, which we said is the summation of what? Our xi minus the expectation of x, like that, and we square that. So we need to find what that is, then we'll substitute that, and then we can maximize from there. And by definition of expectation, right, this is simply equal to integrating from 0 to what? To 1, because our x is between 0 and 1 there, just in case it's not very clear, between 0 and 1, so 0 and 1, and our PDF is 1 minus theta, and we have x to the power minus theta with respect to x, since it's the function of x, right? Then again, this should be now simple to find the expectation of a random variable. And if you simplify that correctly, you would get that our expectation is equal to 1 minus theta over 2 minus theta, like that. And once we have that expectation, now we can go on to complete our function q, which we say is simply just the summation of our q of our xi's, right? So our q is equal to the summation from I equal to 1 to n of what? Xi minus the expectation, which we now have as 1 minus theta over 2 minus theta all squared, right? And the next step here is for us to find the first derivative of this. Because for us to maximize this, it requires us to take the first derivative and we equate that to 0. And when you take the derivative, you would have to use the chain rule, which means we are going to have this 2 here, will come down here, and we have the summation from I to 1 to n. You write this function as it is, 1 minus theta, 2 minus theta, and you have to now multiply with the derivative of the function that you have there. Again, remember, the reason why we do that is because we're using the chain rule. And when you do take the derivative of this term there, you'll find that the answer you get is 1 minus 2 minus theta squared, like that. And we have to equate this to equal to 0. So these two terms, this 2 and that, are simply just multiplying this summation sign here. And we're equating this to 0, which means I can divide both sides by 2. I can also divide both sides by 2 by this term that I have here, so that I am left with a summation from I equal to 1 to n of xi minus 1 minus theta over 2 minus theta. And I wanted to talk about this here, that whenever you're doing your estimating using the method of least squares, it will always happen that in the end, what you will be equating to 0 will simply be just this part here, excluding the 2 there. The reason why we just follow the steps that we're doing there is because, as the name says, the method of least squares. So you first need to show what function you want to maximize, and hence you go through the whole process, and then, but this will always end up falling out, and what you always just have is you equating the summation of your xi minus the expectation that you have there. And to complete that, I would distribute the summation sign there, so that I have the summation from I equal to 1 to n of my xi minus, as you would expect, that if I am going to be summing from I to n of this term here, which is not really dependent on any variable, I would end up having my n multiplied by 1 minus theta over 2 minus theta being equal to 0, right? And from there, I can divide by n throughout. I can divide by n throughout, so that this just becomes what? X bar being equal to 1 minus theta over 2 minus theta. And after that, all you have to do is to solve for your theta, right? That's just now some math stuff, where you just have to solve for your theta to make it the subject of the formula, and you get your answer would be 2x bar minus 1 over x bar minus 1. Like that. Okay, so you get that point there, and you get that being your answer. And there's something that I'm just looking for here. Quickly, give me a second. Something important I wanted to mention. Okay, oh, there's a question. Hold on. I don't understand why we just left the summation. Oh, okay. Let me quickly explain that part there, why we just left the summation. So what I did is that, I hope you were fine with the parts that we had there. What I did was to distribute this summation, right? Meaning I took my summation from I equal to 1 to n, right, of my xi, because by distributing, I mean I'm going to take the summation of that minus the summation of the second term, which means I'll have the summation from I equal to 1 to n of what? 1 minus theta over 2 minus theta, like that, okay? And this term here is like having the summation from I equal to 1 of n with what? Let me just say, yeah, theta itself, right? This is just saying you're going to have theta plus theta plus theta plus theta, and you're doing this n times, right? So it's just going to be the same as saying n multiplied by theta. And this the step above. Okay, the question was, I don't understand why we just left with. Oh, okay. I think I understand your question now. I understand your question. So the question is why we are just left with this section here. Let me write this clearly. Our Q this year was 2 summation I to n xi minus 1 minus theta over 2 minus theta multiplied by what we get when we take the derivative of the inner function minus theta all squared, right? So this is the same thing as me writing it in the following way as being 2 over 2 minus theta all squared summation I is equal to 1 to n of xi minus 1 minus theta over 2 minus theta, right? Being equal to 0. So that's what I've just done now. After we took the derivative using the chain rule, we have the summation multiplying the 2 and multiplying by that. So I first multiply the other terms together, 2 times that, and I have this here. And now this is like saying, what do I want to say? This is like saying 2 plus x plus 2 is equal to 0, right? So what I've just done, that now, instead of just having x there, I actually have something in the form of the summation of xi minus theta being equal to 0. But what I want is to have theta as the subject of the formula. So I'm going to divide throughout by 2, right? I'll divide throughout by 2. If you want, you can just multiply them separately first. To have 2 times the summation of xi minus 2, the summation of my theta being equal to 0. Then you divide by 2 all the way. Well, there's a 2 there, there's a 2, but there's a 0 there. So you end up with just xi minus the summation of my theta being equal to 0, which this here will just be n theta. Okay, I hope that makes sense. Awesome, cool. Let's move on. So where we were, we ended up having that we ended up getting that our estimate, right? Okay. We ended up getting that our estimate was equal to, this is what we got. We got this here being equal to 2x bar minus 1 over x bar minus 1, like that. So in a question where, because I can't find what I written down here, my papers are just all over. But what I remember was that now, if you were asked that find, oh no, I actually see what I find it, but we'll come back to that. We'll come back to it. So what you do, the next part of the next question here, this is actually like a typical exam question, just to show you how easy this section can be when you're asked in an exam. Okay, you're given your x1, your x2, and then it goes to x4. Then you're told your PDF of x is simply just equal to 1 over beta e minus x minus 4, right? I won't really do this question here I'll just explain what happens. And x is greater than 4 and is 0 here otherwise, right? This is our PDF as is given there. And the first question, before we even get to the question, we are given some data points. And you have 8.2, you have 9.1, 10.6, and you've got 4.9, like that. And they are so nice that they give us the expectation of x being equal to beta plus 4. And again, you're just going to find the list, the method of least squares estimate of your beta, right? So just to talk through what we are supposed to be doing with this method again, it's just a matter of us finding the function q, the summation from I equal to 1 to n of what? My xi minus its expectation all to the power 2, right? And then you will need to take the first derivative of this here, which will be equal to, so this is something that you can even do before you start plugging in like your expectation. So that this here will be a 2, or actually you need to find that, you need to put that already so that you can have something to multiply with there. That is our q is I from 1 to n, the xi minus b minus 4 all squared. So all I've done here was to say minus the expectation, and the expectation as it's given already is beta plus 4. So I've already put that into effect there, and hence I have that. Then what follows is you finding our q1, the first derivative of that, which will still just be equal to 2, summation I equal to 1 to n of our xi minus bu minus 4 multiplied by the derivative of this here, which is a minus 1. That is a minus 1, right? Because the derivative of beta there will be minus 1. And from there, this is simply just minus 2, the summation I to 1 to n of xi minus b minus 4 being equal to 0. I'll divide by this both sides such that I'll be left with the summation from I equal to 1 to n of my xi minus b minus 4 go to 0. Just to show you guys what I was saying, that in most of the cases, though this is what's given by definition, since it's a method of least squares, you need to show the squares and whatnot. But at the end of the day, what you're going to be really working with is simply this term here, the summation of your xi's minus its mean after having taken the 2 down, and it disappears, and you end up just working with something like that there, where you're going to distribute your summation sign to your xi, your b. So this will be just n, bn, beta n, then this here will be 4n, like that. But then now you have to use the fact that you are given your data. So instead of just saying n, you have 1, 2, 3, 4, and you've got your xi's, and you still just follow the same procedure. And from there, you will get your estimate. Cool. So I want us to quickly also go over the method of matching quantiles. Again, also quite a relaxed method, right? Not very difficult. And it goes as follows. Method of matching quantiles. It tells us the following. I will write 3 lines of summary for it. Then we get into an example, which I want to join it together with something that we've already looked at, which what I was saying I couldn't find the paper of. So we're saying the method of matching quantiles, right? And what this method tells us, right, are the following steps. 1, what you have to do, find the CDF. Find the CDF of your model. Find the CDF of your model. Once you've done that, set your CDF of x evaluated at this population quantile, and you let that be equal to p. Then you simply solve for your population quantile, right? So again, this is something which sometimes can be given in words, where they will say maybe the lower quartile or your upper quartile, just knowing your lower is 24 a quarter, your upper is 3 quarters, then your median is half. So what this is just saying is that if you're given a model, find its CDF, right? If you are looking for the lower quartile, this will be E 0.5, right? Which means you're going to now take your f of x substitute this here, right, as a variable like that, and then this will be equal to that 0.25 there, and you simply just have to solve for that there, and you get your answer, and that will be your estimate in that case. So what we are there, just to put this here into practice, we'll write a function, right? This is quite another popular function, I think I've used it already. We have theta plus 1 and y to the power theta when our y is between 0 and 1, and then 0 otherwise. And it goes further to ask you to find the method of matching quantiles estimator, right? Estimator for theta. And then another, on a side note, it says use the median. Says use the median. Use the median. Population quantile here will be E this year, and then there'll be a 50% there. So the first thing, like we mentioned, you need to find your CDF of X, right? Find your CDF of X, and we know by definition, the CDF of X will be from 0 to Y of our PDF, which is theta plus 1 t to the power theta dt. So you use y, but I just used my t's there since I have a y on the upper bound for my integral. So this here simplifies to being y to the power theta plus 1, okay? And the next step, so this is our CDF, right? Obviously, it's not as simple as it's actually not a difficult function, but you just do some work taking that out, but your final answer should be that, right? I don't like assuming, but I just want to, in this case, assume that everyone understands how we get the CDF. And the next step tells us that you equate that CDF after you first evaluate, you evaluate this at this population quantile and equate it to the probability that you have there. Which means our next step, since it says use the median, what we do is actually taking our CDF, which is that there, right? Our CDF of y, and we evaluate it at 0.5 being equal to 0.5, like that. So this is actually just E 0.5 all to the power theta plus 1 to be 0.5, like that. Okay. So some questions, in some papers, this can actually just be written as X median, like that. Because this is the median, 0.5. Then the next thing we do is to take ln on both sides. Ln of this here to the power theta plus 1 be equal to ln 0.5. Then that is just theta plus 1. And we have our ln 0.5 be equal to ln 0.5. That's that. I hope that's okay. What I've just done is to take ln on both sides, and after taking the ln, I took this down there. And the next thing that you just have to do is to simply solve for our theta, right? So in this case, I would have that my theta plus 1 is equal to ln 0.5 over ln 0.5, like that there. This is still there. Therefore, my estimator is simply equal to ln 0.5 over ln that here 0.5 minus 1, which is equal to ln 0.5 ln 0.5 there minus ln that 0.5. Okay. Again, this is just one of those methods that it's not difficult. Finding your CDF, you substitute that there, and then you end up getting your answer. Cool. Then just to quickly, it's a quick refresher. If then the next part of the question is like find the method of moments estimate of your theta, MME of theta, right? Just wanted to refresh this quickly because we're going to use it. And remember, what we do with this method here is that we first have our theoretical and then our observed, and we equate the two. And like I mentioned, if it's not sigma, we will always work with this method here, being equal to x bar, right? And our x bar is a matter of finding the expectation of y. I don't know why I was now using x, but we're given our function in terms of y. So you find the expectation of y in this case 0 to 1, because our y was between 0 and 1, multiplied y multiplied by the PDF, right? It's still the same function, that dy, and you get theta plus 1 integral from 0 to 1 of our y theta plus 1 dy, and you find that your answer is theta plus 1 over theta plus 2. So straight up from there, what you just have to end up doing now is to remember you are taking your theoretical first moment being equal to this x bar. So we have theta plus 1 over theta plus 2 being equal to x bar. And what you need to do is to make theta the subject of the formula such that our estimate will be equal to 1 minus 2. Okay, I'm back to using my x's again. So this is supposed to be y. So this is in a final 1 minus 2 y bar minus 1. Okay. Then what I wanted to get to as well was that now the next part of the question is, this is just a small refresh of a full question which should come the way I'm going over it now. Then the question is now saying, C, use the delta method. Use the delta method to find the variance of this here, right? Of which we're given this being 1 minus 2 minus y dash over y dash minus 1, right? And it's important, again, like I mentioned, remember, this function that you have here, what we have is a y bar and a y bar. So from that, this year, our h function will be h of y bar as well. Not h of theta, but rather h of y bar. And to move on from there, what you then do is that by definition, the variance of this should be equal to the first derivative of this y bar that you have, all squared multiplied by the variance of the same y bar again, right? The same y bar, because according to the definition of it, and from there, if you work out your y bar there, the first derivative of our y bar should turn out to be just equal to 1 over y bar minus 1 squared. And then the variance of y bar, something that I just wanted to quickly touch on because that will be important. It's just that here we are given information about y and not y bar, but it's very easy to move between y and y bar in the sense that the variance of our y bar here will simply just be equal to the variance of what? 1 over n of the summation from I equal to 1 to n of our yi, like that. Which this here is simply equal to 1 over n squared, right? When you take it out there, you have to square it, and the summation from I equal to 1 to n of the variance of our yi, like that. So now part of the question here would now go to you finding what the variance of our yi is, right? You find the variance of our yi because we have this already. So the variance of yi, you can even just find what the expectation of y squared is. Then when you have that, you use the definition that we know that this is just y squared minus the expectation of our y all squared. So what I just wanted to stretch out there, there's nothing new that I'm saying that you don't know by now, but I just wanted to stretch out specifically the point where you now need to find the variance of your y bar, just to remind you that you can simply just break that down to be in terms of an xi to cancel. So your answer will have to just be a 1 over n and the variance of y. Okay, this is something that's very easy to do. And just for more practice, when you go over your 2019 paper, test 2, you'll see that they still that parameter that I mentioned earlier on called for x bar over 3. Okay, exactly what I'm saying here is what you end up having, because you also want the variance of your y bar here. Actually, the answer will be, what you will use for this is exactly this here, right? And you will need the variance of y bar, and you do it the same way where you're going to break it down to be a function in terms of our y, and then you just work from there to get your answer. Cool. Are you guys following? Is everything okay? Let's see. Okay. The last part with the multiplication of n. Okay, so what I was just saying is that as you see again as well when you are doing your past papers, is this here we have the variance of 1 over n, the summation of xi, like that. Okay, then we say that this will be equal to 1 over n squared, the summation of the variance of our xi, like that. So before you even change that to an n, you can go on to find what your variance of your y is. You go on to find what your variance of y is. Maybe you will find that the variance of y there will be theta. Okay, why am I using theta now? Yeah, maybe it will be some function, but from that function you can definitely see that it's a constant and not a random variable, right? Maybe it will be something in the form of theta plus 1 over 2 minus theta, something like that, right? Which means this will be 1 over n squared, the summation from I equal to 1 to n of this function here, which is not a random variable and is not moving from I to n. So instead, it's like adding this here n times, which will now just be equal to, this will just become an n over n squared multiplied by the function that you get as your variance, and then that will cancel, and you'll be left with one n there. So your answer will just be 1 over n and the variance that you would have gotten there. Awesome, cool. Okay, now the next thing that I want us to quickly look at cool. That's the next thing that I want us to look at is the numerical computation of MLEs, right? So we are looking at a numerical computation of MLEs. So this is very important. Okay, yeah, it is important, and it's something that they recently started asking in questions. I guess this was never tested with us, but numerical computations of MLEs, right? You are not able to find that MLE directly. That is by getting your likelihood function, your score function, and then you equate your score function to 0 and solve. And in this case, we're saying, well, the same way in the case where the range was dependent on the parameter of interest and you're not able to solve, even in this case here, even though maybe your range is not dependent on the parameter of interest, but you find that you cannot actually solve for your parameter, for your MLE, then we use these two methods that we have there, where the first one is our Newton. This is our Newton Raphson method, and the other one is our Fisher, what do you call it? It's our Fisher scoring algorithm. So these are our alternative, right? But again, it's not just something that you need to worry yourself about, wondering whether, okay, so since I need to first see if I cannot find the MLE, then you need to consider this. This here will be explicit on whether you need to use it, in the sense that you will need some other estimates, like previous estimates that you will need, as you will see when I write the definitions there. So this will actually kind of be explicit when you need to use it or not. And if I were to quickly just go to write the formula for the Newton-Raphson method, it tells you that like your iterate, right, will be equal to the previous one minus the score function evaluated at this year, or divided by that theta m minus 1, like that. Okay, so I just want to quickly explain what's happening here. And what's happening in this case is simply just that for you to find this here, they'll even tell you how many iterations you need to have, right? They can say find 2 iterations, which means, as you can see, this second iteration will depend on the first iteration. Therefore, the first iteration will depend on if I can call it the 0 iteration, right? Which means I would have something like this here. So they'll always give you a starting point, right? A previous point, which will help you to calculate the next point, which that point will help you calculate the other point. Okay. So what you just have to do is still in the same manner that we went about our MLEs. You need to go find your likelihood function. You find your score function, which this score function is simply the first derivative of your log likelihood function. Right? And after that, your information function here is simply the second derivative of your log likelihood function. So as you can see, it's very much related to maximum likelihood estimate procedure in the sense that you will still need your score function. You will also need your information function. So now it's actually as simple as being a matter of you being able to then be, after given the first maybe theta naught, then you want your theta 1, your theta 1 will be equal to theta naught minus your score function, right? Your score function here, you evaluate that at theta naught divided by the second derivative of your log likelihood function at that theta naught as well there. Then you just simply plug that into your calculator and you find your answer. Then you continue for your theta 2 as well, but now you'll be using your theta 1. So that's basically all about it. The only part where that I can think of, because again, like I mentioned, this will probably the first step they're going to be testing this year in tests. And this kind of questions is when maybe the procedure of you finding your likelihood function there. You'll be given a density, which can be a bit difficult to work with. But the nice thing about most questions where it's difficult to find a function, a density, which you maybe need to use below, is that they will let you, when they're asking you to find that, they would say, show that maybe your log likelihood function is this. So it will be given, and thus you'll be able to actually answer this question and then still be able to fight back to see if you can get back to that function which you are saying you should show. Okay. Then the next method is your Fisher scoring algorithm, right? Which is given as follows. Very similar as well, and but then the main difference is that here, instead of subtracting, we add the same function, right? Theta m minus 1, like that. But now you are going to divide with the expectation of this function that you have as a denominator here. Okay? So it's almost the same function. It's almost the same function, except that here now you're adding, and instead of dividing by this, you're going to find the expectation of that. So it's something you can definitely expect to be asked a question where obviously you'll be given a density, find your MLE, not MLE, I mean your log likelihood function, your second derivative, then you plug into this here using your Newton-Raphson method. It's very likely that after that, a follow-up question would then be asking you to use the Fisher scoring algorithm. Because why? It's very much similar. Already, for your first iteration, right? For example, for your theta 1, you would already have this term there. You have that term, but now instead of subtracting, they're going to add this term here. You would have it already. The only difference is that where you had this term, you are now going to be taking the expectation of that. I think it's actually supposed to be the negative expectation. Sorry, it's supposed to be the negative expectation. I'm going to put an X there again, because now if this function as well has some random variable in there, you also need to take that into account. Okay, yeah. So that's basically one of the things that you need to really understand there. And one other question they would ask you is about convergence, right? To ask you if convergence is achieved. And to answer this here is just the basic definition of what we described our convergence to be, and that is literally the distance between a random variable and some number getting smaller as n approaches to infinity. So all you have to do is to check if the distance between your mth iteration and the iteration of your m minus 1 here is sufficiently small. This is not really there isn't a range that we can say is sufficiently small, but one thing you will notice is that when you find these iterations here, you get numbers like as follows. You'll be getting numbers like 0.6657 and 0.6523, something like that there, which when you take the difference there, you can see that most of the times it will always be very, very small. I guess this is something also that you can just confirm with the tutors if there is a range, but from what I can imagine from these numbers that you can get there is that this will most likely be very small, as you can see there. Then you can conclude that in both the methods, right? This is the condition in both the methods, that if the distance between your m and your m minus 1 iteration is sufficiently small, then you can conclude that convergence is achieved in the method like that. About that. Then another thing that I would really just like to outline, which is very important as well, but this year, if it comes, it will be like a small marks. It's still going to get deeper into this when you get into the other sections that are left, probably for your exam. But even for this year, a small part of it can be asked, and that is the concept of bias, right? The concept of bias, or rather, let me say, being unbiased, right? And there are two terms that I want to talk about. So we say, so what we do, you find your maximum likelihood estimate, and now you're checking whether it's biased or unbiased, okay? And suppose you've got a distribution X here with parameter of interest theta and theta E minus theta X, like that, our exponential distribution. Definitely, clearly our parameter of interest there is theta, right? Then the question could be, you can find an MLE, right? You find an MLE of your distribution there to be that. And now my statement is that this MLE here will be unbiased. This here will be unbiased if, right, the expectation of the estimate that you are having there is equal to the parameter of interest. Okay, so what I'm basically saying here is that you found your maximum likelihood estimate, and now you want to check whether it's unbiased or is it biased. And the condition is that if for your estimate to be unbiased, right, it means that when you take the expectation of that estimate that you have, it should be the same as the parameter of interest that you have here, theta, like that. So I'm saying take the estimate of this, it should give you that, the parameter of interest. Otherwise, that will not be unbiased. It will be biased in that case. As well, we also talk about being asymptotically unbiased. Asymptotically unbiased, right? And this here tells us that this is true if the limit as n goes to infinity of the expectation of theta is just equal to theta, like that. So the difference there is that one will be taking a limit. If it specifically asks you if it's asymptotically unbiased, this is the condition you need to show. But if the question is just asking for bias, then all you have to do is to show that this is true, okay? Then just to quickly note this part here, that a question could ask you, okay, the question could be like, find if this estimate here is unbiased or not, right? And like we're saying, this here, for it to be unbiased, it means it must give us theta. But let's consider a case where you actually get k theta, like that. Okay, so this can happen, that a question asks you to check if the estimate is unbiased or is it biased. You take the route that we said here, you need to take, that is, take the expectation of that estimate, see if it gives you the parameter of interest of your distribution. But it happens that in this case here, instead of giving us that theta there, this expectation is giving us k theta. Then a follow-up question straight up from there, we could ask you, what is the unbiased what is the unbiased estimator, okay? And all you have to do is to find a function such that when you take its expectation, it will give you theta. And straight up, estimator will simply be equal to theta over k. This will be unbiased. I will prove it to you why it's unbiased. This is unbiased because the expectation of theta over k will be equal to 1 over k multiplied by the expectation of theta, which we have found there to be k theta over k, which this is just equal to theta, like that. Then hence I say that is unbiased, right? So remember, what's just important is that when you are trying to check if an estimator is unbiased, you take its expectation, it should give you the parameter of interest. If it does not give you the parameter of interest and gives you some function there, all you need to do is to find a function such that now you will take that into effect as it is. So now this becomes a fact, right? And what I mean is that when I got to this point, when I found the expectation of theta, I actually used what we got there to be k theta, and hence I divided by k there. My point is, once this happens, you need to find a function such that when you take its expectation, you will get your theta. So that means if this here was actually expectation of that being equal to theta over k, right? This means my unbiased estimator was now just going to be equal to theta multiplied by k. Why? Because when I take the expectation of this here, this will just give me k multiplied by the expectation of theta divided by that, divided by that, which will just be equal to k multiplied by theta over k, like that. Such that this and that will cancel, and I'll be left with just a theta now. Yeah, can I just get an indication if what I've just said here makes sense? Awesome, cool. So then the next thing that I wanted us to just quickly look at, nothing hectic, it's just still on this bias stuff. Cool. So you could even just be given a distribution, right? Let's say you're given your distribution f of x and theta. Then you're told that this is mx theta to the power x 1 minus theta to the power m minus x, like that, where x 1, 2 to m, then this is 0 otherwise. Then you are given two parameters, theta 1, and let's say this here is equal to x1 over 2. Then we have this other one being equal to theta 2 being equal to x1 plus x2 over 2m, right? Rather, let's have this here being equal to x bar, like that. Cool. So now what we do is the question could be asking you to check if these are here are unbiased parameters, right? Oh, before we go there is something that I always just want to mention, which is this here about being consistent, right? Consistent, and theta, your estimate will always be consistent if your theta here, your estimate converges to what? Converges to theta in probability, right? And this is something that I doubt they will ever really ask you to prove. Why? Because there's also another theorem which tells you that every MLE is consistent. There's a theorem in your notes which mentions that. Oh, the range that I have here is just that my x is moving from 1 to m. my x is starting from 1 all the way to m, like that. Cool. So what I wanted to mention is just this fact here, that just to know it, in case they do ask, there's a proof for this here which says that every MLE is consistent. But for an estimator to be consistent, this simply means that what is the exponent of 1 minus p? Oh, this is equal to m minus x. So basically, what I have here is the binomial distribution. X is equal to 1 and 2. That's a binomial distribution. That's what I have there. So about consistency, so an estimator here will be consistent if it converges to the true parameter in probability, right? And you need to go and revise how to show this convergence here, right? It's just a matter of showing that the limit as n goes to infinity of the probability of xn minus, okay, not xn in this case, but rather the estimate minus that being greater than some epsilon is equal to 0, right? Where you would have to use Chebyshev's inequality to solve this other part here, okay? So again, if you can just show that this estimate that you have actually converges to the true parameter in probability, then you would have shown consistency, that your theta, your estimate is consistent. Then there's another theorem here which you can just check out the proof in case it ever comes up, which says that an MLE is always consistent, which means that the MLE estimate here will always converge to the true parameter of the distribution in probability, like that. Cool. So the reason why I put up this here is just for a question that could give you a distribution like that as part of the question. Actually, this will not be a full entire question, but this could be something which will be asking you to check if these here are unbiased or not, okay? And the expectation, so for this to be unbiased, like we said, is a matter of checking if its expectation, right? The expectation of that estimator is equal to the parameter of interest, which again, in that case there, is our theta. So that's what we want to check, okay? So if we're using lambda, if the parameter of interest was lambda here, it means we're going to be equating this here to be lambda, but again, this is equal to theta, okay? So now the expectation of our theta 1 here will simply be equal to what? The expectation of x bar over 2, right? The x bar over 2, and this here will be equal to 1 over 2, the expectation of your 1 over n xi, like that. So I'm sure you can see here that it's very important for you to get used to when you want to find some information about an x bar, to quickly then transform that to an x problem, an x variable problem, which will be equal to 1 over 2. Then I'll take this, okay, I will not have an n here, I'll have an m because my x's are running from I to m. So I have an m, 1 over m multiplied by that, such that this will be an expectation of 1 over m, and my summation of what? My summation from I to m of the expectation of x. And we know that our x is the binomial distribution, which means its mean is just equal to what? NP, but in this case, that's m lambda. Oh my God, I've been doing funny things there. So my expectation of x is just going to be m theta, right? Because that's a binomial distribution. So what I would have is 1 over 2m, right? And then the summation from I equal to 1 to m, the expectation, like we're saying, will just be equal to theta m, like that. Then what follows straight up from there is the fact that this will be equal to an m squared theta over 2m. So this is equal to m squared, was my m, this m here, and this m will just become an my, because I'm going to be adding this here m times. So this will be m squared theta divided by 2m. That m will cancel and there is an m here. So what we actually end up having is m, where we have m and we have a theta over 2, like that. which which in this case here is definitely not unbiased. This is biased because what? We are not getting the parameter of interest that we wanted, which is theta, but here we have that. So if a question then asks you to find, and if the question then asks you to find the parameter, the estimator, which is unbiased in that case, you just have to work around with what you have there, because now we know that the expectation of this theta 1 here is actually just equal to what? M theta over 2. So you need to work around such that you get a function. When you take its expectation, you end up getting theta. And that function should be something which should be 2 theta over m, right? You can just check this, or if it's not exactly that, you can always work around to make sure that all you want is to manipulate it to get a function which is going to be, its expectation will be theta when you check its expectation. Again, this is a question that this is a section I'm not 100% sure they'll ask you yet, but I saw in your notes there is something about being biased and not being biased and unbiased. And since the condition for being biased is given, right, telling you that for you to be biased, this has to happen, it's very possible that you can even be asked then to provide an estimate which will be unbiased based on what you would have found to be biased. Okay, so then this is probably the last thing that we're going to look at, which is just the expectation of our theta 2, right? This is simply going to be the expectation of our x1 plus x2 over 2m. I will take the 2m out. Why? Because that is a constant in this case. So this will give us 1 over 2m multiplied by the expectation of x1 plus x2, like that. But we know that the x1 and the x2s are both coming from a binomial distribution with the parameters which are given from the density there. So I can actually separate this to be 1 over 2m multiplied by the expectation of x1. Expectation, okay, I will have the expectation of my x1 plus the expectation of my x2, right? This is all divided by 2m, such that this here will be equal to what? M theta. So I will have M theta plus as well here M theta divided by 2m. So what I end up having is just a 2m theta divided by 2m. Then that here will just simply be equal to that, and that will cancel, that will cancel, that will cancel, and we get a theta. Then our conclusion will be that the estimator that we have there, theta 2, is actually unbiased. Okay, so now, okay, we still have like 10 minutes left. You guys are free to call it a day. If you're calling it a day now, I'll just wait for another 10 minutes to see if anyone has any questions that they would like answered here. Well, you guys still there? Oh, cool. Yeah, so if you just have got any questions, please do let me know. And good luck for your test, guys. At least I heard that you've got like an extra week. I hope that's a good thing. Yeah, good luck. Theta. Oh, cool. Okay, sure.
Those ones are for cooking. Yeah. You will get that energy.